The Michelson interferometer and its modifications are used in the optical industry for testing lenses and prisms, for measuring indices of refraction, and for examining minute details of surfaces. In this session we are particularly dealing with 4 applications in which we can use Michelson's interferometer to determine wavelength of given monochromatic source if light, refractive index and thickness of various thin transparent material, resolution of spectral line, difference between 2 neighboring wavelengths for measurement of standard meter in term of wavelength. We will deal with them O and D by 1. We can use interferometer to measure the wavelength of the monochromatic light source lambda. For this the mirrors M1 and M2 are exactly perpendicular to each other, and for we observe through the telescope we can see circular fringes. If we move mirror M1 backward, circular rings will appear at the center. And if we move mirror M1 backward, rings disappear at center. Let's move mirror M1 through D distance. We count the number of fringes disappearing at center. Initial thickness of air between mirror M1 and image of M2 BD1 correspond to M1th bright fringe. D2 final thickness corresponding to bright fringe of order Mn in same position. We can write condition for bright fringe as 2d1 equals m1 lambda equation number 1 and 2d2 equals mn lambda equation number 2. Equation 2 minus 1 we get 2d2, d1 equals mn, m1, lambda. d2 minus d1 us the distance covered by mirror m1 which is d and mn, m1 is the number of fringes disappearing which is n, then we can write above expression as 2d equals n lambda. On rearranging equation we get expression for wavelength of light as lambda equals 2d divided by n. As long as we count the number of rings disappearing or appearing as we move mirror through the distance d, we can find wavelength of light source. Another application is to find difference between 2 wavelengths. If the source we are using is not strictly monochromatic, but consists of 2 wavelengths lambda 1 and lambda 2. We can find the difference in wavelength using interferometer. Mirror M1 adjusted to obtain position where fringes very bright. This happens if bright fringe due to 2 wavelength coincide. Now move M1 apart from position, at certain position no fringe observed, that is dark fringe due to 1 wavelength coincide with bright fringe due to other. Again move M1, fringes become very bright. Possible when mth order of longer coincide with m+1th order of shorter wavelength, as m1 moves through d distance between 2 consecutive maxima. m1 and m2 changes I the order at center. We can write condition for maxima as 2d equals m1 lambda 1 equals m2 lambda 2. If lambda 1 is greater than lambda 2 then m1 plus 1 equals m2. On substituting we get 2d equals m1 lambda 1 equals m1 plus 1, lambda 2. On rearranging equation we get m1 equals lambda 2, lambda 1 lambda 2, and 2d equals lambda 1 lambda 2, lambda 1 lambda 2. Difference in wavelength, lambda 1 lambda 2 equals lambda 1 lambda 2 slash 2d. This is an important expression. If we need to find the thickness if a thin transparent sheet, we have to place the sheet in path of light ray towards M1. This will change the path difference. The ray will travel twice through the transparent sheet of thickness T and refractivity index mu. Optic path of beam increases to microtesla. Increase in optical path is microtesla minus T. Since beam transverse twice in medium path, difference equals 2 times microtesla minus T equals 2T times mu minus 1. Fringe system displaced by m fringes, then 2T, mu, 1, equals m lambda. On rearranging equation we get thickness of thin film equals m lambda divided by mu, 1. To obtain this value m, we will first coincide crosswire a bright fringe. Now thin film is introduced in path of beams, there is shift in pattern. Fringe system will be displaced by m fringes. This is counted. Knowing value of m, refractive index of material and wavelength of light, we can find thickness of film. Another application of Michelson's interferometer is the determination of refractive index. Tube of length L containing gas of unknown refractive index is introduced in beam path going towards M1. The path difference changes. Change in path difference 2 mu, 1, L, the fringe system get displaced by m fringes. Then, 2 mu, 1, L equals m lambda. On rearranging equation we can write expression for refractive index of gas as mu equals m lambda by 2 liters plus 1 refractive index at various pressure can be determined using this setup.